Okay, cool. Well, hi everybody. I'm Braxton. I'm here to talk about evaluating the quality of student-written software tests with curated mutation analysis. I worked on this with Elisa, who is in the chat somewhere. Um, but before we get into it, I would like to acknowledge that this work was conducted on the traditional, ancestral, and unceded territory of the Musqueam people. And also, before we get too far into it, I need to give you a little bit of context. So we're over at UBC in Vancouver, Canada, and we teach this big software engineering course. And we pipe about 600 students through the course every term. Every year, so 300 a term. And the students are assigned one thing that they really need to do, project-wise, and that is make a big full-stack web application. It's a pretty big project. It's like about 2,000 lines of code on average, and it takes the full 12 weeks for them to do it. The first 2 weeks is the testing phase. And in the testing phase, the students don't have an implementation yet. They are just given a specification, and they're told, go write unit tests for the specification, and we'll give you back a score. Following that, bootstrapped with only their tests, they pair up with a friend or a stranger, or maybe enemy, and they start building the full thing. And that takes the remaining 12 weeks. But that phase isn't super important to us. What we want to look at for this talk is the testing phase. Again, it's black box testing. They don't have an implementation. We grade them using a reference solution, which we wrote, so it must be perfect. There are a couple learning outcomes. The ones that matter for this talk are: one, learn to write a test suite that finds faults; two, learn to check the behavior of all code that was invoked; and three, learn to refine a specification into a test suite, something that is a machine executable specification, you could say. But that's not how the students see it. They see it as, I'm going to read a specification that's really poorly worded. They always complain about it. It's not true. We're very careful about this. I'm going to write unit tests for a system I don't exactly understand, and I'm going to stay up all night doing it, and then I'm going to send my broken code off to the autograder, and the autograder will take the student tests and take the perfect reference solution and put them together to squeeze out a score. The students are never happy with the score. And then they do this over and over again, and well, not until they're happy, that's what it says on there, but until the deadline passes is actually when they go until. But what we care about for this presentation is the score. How did that get made? Where did that come from? What we used to do was use code coverage. We all know code. I mean, I'll explain it again for the none of you that don't know what code coverage is, but I have my code under test, and I have my tests which invoke said code, and the number of statements that were invoked by the tests over the total number of statements in the system entirely is the code coverage score. That's statement coverage. You can always use line coverage or branch coverage, but we used code coverage. So in this example, add one takes a number and then adds one to it and returns it. Very simple. And that test suite over there, which is comprised of exactly one unit test, according to code coverage, is a perfect test. A perfect test suite, even 100% code coverage. But anyone paying attention would notice that if add one actually added two, or subtracted one, or didn't even give you back a number, really, should add one would still pass. This is probably not a good test suite, even though code coverage is claiming it's the best possible test suite. So before we look into alternatives, let's look at code coverage in terms of those, in terms of the learning outcomes we were looking at earlier. So learning to write a test suite that finds faults. Are we evaluating them on this? Yes, because code coverage is highly correlated with fault finding ability. So we are kind of getting a fuzzy look into whether or not students are writing a test suite that finds faults. We also want to know if students are achieving checking behavior of all the code that's invoked. As we just explained, we don't have any window into that at all, which seems a little weird. And next is learn to refine a specification into a test suite. We say we're grading them on their ability to cover a specification in tests. That's not exactly true, because let's say I have a specification. It has two requirements, requirement A, requirement B. Both are equally important to the system. Both are equally difficult to reason about conceptually and equally difficult to implement and test for. Should be, they're probably worth about 50% of the grade. However, in my implementation, the reference solution, which again we wrote and is perfect, let's say implementation A is, subcomponent A is very concisely implemented. Subcomponent B is very verbosely implemented. Then subcomponent B ends up becoming worth a lot more. So we're not exactly grading them with what we said we're grading them on. It's not about specification, it's about the implementation, which they don't even get to see. That's very frustrating for a student. Other considerations, code coverage is very fast to compute, which is good. And it doesn't take a lot of instructor effort to get it running. You type in Y, C, cov, or whatever your CLI interface is, and it should work. But again, the fact that we're not doing the right thing is frustrating for us. And they also knew that. The students figure it out every term. In the first 2 days, they ask the same question: does my test actually need to be right for me to get a good grade? And we begrudgingly respond to them, yeah, you're right, you don't need to make a good test. So we started looking at alternatives, entering mutation analysis. So mutation analysis, for those of you who don't know, is, let's say, again, I have this code under test. And one thing I could do is I could duplicate the code and make a tiny little change to it. In this case, I'm going to take the plus and make it a minus. This duplicated code with the change, this is the mutant. And we want our test suite to be able to detect that a mutant was created. So this new test suite is a little bit better. This one has an assertion in it. It's checking that adding 1 to 1 actually does equal 2. So mutation analysis does say that this is a good test suite because the mutation score is calculated by the number of mutants which were detected over the total number of mutants. The literature is a little violent. It likes to call detecting a mutant killing it. That's what's on the remainder of the slides. That's what I'm going to go with. Mutation analysis. Now, in terms of our learning outcomes. Learning to write a test suite that finds faults. Well, there are faults being injected that they must catch or kill. So yeah, we are evaluating them on that. Learning to check behavior of all code that is invoked. If they don't write the assertion, they don't get the mutant score. So we are evaluating them on that. However, we still have the problem of specification versus implementation, because generally mutation analysis is something that is done automatically. You would use a library that walks over your code and just generates as many mutants as it can. And one traditional way of doing that is looking at the AST and looking for terms in the AST and making little changes in there. So if you have a verbose subcomponent, it's a big AST, and that means it's worth a lot more of the final mutation score. Other considerations: is it fast enough for autograder feedback? No, because this automated mutant generation, you're normally making something on the order of like hundreds of thousands of mutants. And we have a really big project, again, that the students are implementing. So running the full test suite once for each mutant to see if a test goes from passing to failing is going to take, I mean, if your test suite takes a second, that's not going to fit on university hardware with 300 students making 5 submissions an hour in the final 3 hours of the deadline. And next, how much instructor effort is there to get it running? The instructor effort's actually really high, because if you were to take a code coverage score and try and turn it into a grade, it's pretty easy. It's just the code coverage score is the grade. But with the mutation score, it's a little bit more difficult to reason about whether or not the student even possibly could have killed the mutant. Because let's say I have, again, add 1, takes n, returns n plus 1. Here I have generated 4 mutants. Which one of these mutants actually is a bug that the student could possibly detect? Which one of these mutants? You don't have to look too hard. None of them. None of these change the input and output relationship of add 1. So that would be unfair for the students if they were graded with that in the mix. So that means that an instructor would need to take this 100,000 mutants that were generated and then manually go through one at a time and decide which ones are real bugs. That's not amenable to autograder feedback. So instead of paring down a big set of mutants into something you can use for an autograder, why not build it up from the bottom? Which is what we did. Curated mutation analysis is a lot like mutation analysis, only the faults are handwritten. We just went in there and took methods and replaced them with faulty methods. Curated mutation analysis in terms of our learning outcomes. We want students to write test suites that find faults. Did they find fault? Well, we are evaluating that because the faults are real. I know they're real faults because I wrote them. Learn to check the behavior of all code that is invoked. Again, they have to write the assertion. Learn to refine a specification into a test suite. We kind of got this one for free, but if I'm the one choosing which faults are to go into the set of mutants, I can tune the set of mutants to match what I think is important in, or I, as the instructor, can tune the mutants to match what I think is important in the specification. So requirement A, I, as the instructor, will give it 1 mutant. Requirement B gets 1 mutant. Requirement C gets 3. Is it fast enough for autograder feedback? Yes, mostly because I only wrote 16 mutants. I couldn't be bothered to write more. Little instructor effort to get running. Also, yes, I mean, more than code coverage, because you have to actually write the mutants. But I'd argue it's not that much more, because normally when you're grading a student on the software artifact they're writing, you define a rubric. I have requirement A, B, and C that I care about. So I'm going to write test A, B, and C to evaluate said software artifact. Here's almost the same thing, only instead of test for the code under test that the students are implementing, it is you write A, B, and C mutants for the test suite that the students are writing. So we built this. It's called the mutation grader. Not that creative with names, but it runs the student's test against the baseline perfect reference solution, and then runs the student's test against the mutants one at a time. And if a test that passed on the baseline fails on the mutant was killed. And the mutant score is just the number of killed mutants over the total number of mutants. If you're wondering how we did this, I mean, it's detailed, but our system is written in TypeScript, which means JavaScript, which means you can do some questionable things that have far-reaching implications throughout the entire system. So this is the identity function. It takes anything and gives you back anything. And as long as that statement on the right over there executes before the tests, identity won't be the identity. It'll be give me anything, and I'll give you back a string. That string, that specific string. So for the remainder of the presentation, I'm going to be talking about a couple cohorts. The first is the coverage term. So this was the final term before we switched to mutation analysis, and we were using code coverage to grade them. And then the mutant term, which is the first term that had mutation analysis. Why we picked those two terms is just they were as close together as possible. They had the same specification, same instructor, same graduate teaching assistant staff, same pandemic. So it should be that they're as close together as we could make it. Naturally, when you get into experiment territory and you want to rush off to answer your questions, you just have the one question in your mind. Did it do the thing that I wanted it to do? Did it make the test suites more good? And the way I was trying to measure goodness of a test suite was just fault finding ability. So the grand thought was, what if I made a bigger curated mutation analysis set? One that you couldn't reasonably do with autograder feedback, because it's so many mutants that it would take hours to run for each student. We did that. We got our friend Nick, great guy, to write the mutation oracle. He knows a lot about the system because he used to be a teaching assistant in the same course. And he wrote almost 100 mutants for us to use. And then we ran it against every student in the coverage term, every student in the mutant term, just trying to compare the fault finding ability of the respective cohorts. And I'll admit this isn't exactly what I wanted to see. For those who can't, well, let me explain it. The people in the mutant term had a peak goodness score of around 65, and the students in the coverage term had a peak goodness score of around 75. Now, I'll come back to this, but usually when faced with data that you don't like, you reevaluate your research questions, or at least that's what I did. So I had some better research questions now. Number one, is the mutation grader an accurate indicator of test suite quality? Number two, does student test quality improve? That's the goodness thing again. It'll be better, I promise. Number 3, do students strive to understand the specification better? Number 4, does the velocity of implementation improve? Now, implementation is the phase following testing, because you'd hope that with better tests behind you, it'd be easier to implement the rest of it. And lastly, what does student tests look like in practice under mutation analysis? That's well, we'll get back to it. Okay, so number 1, is the mutation grader an accurate indicator of test suite quality? To evaluate this, use the same mutation oracle from before, the bigger set of faults, and I compare that with coverage scores and also the mutation grader scores. And the coverage term, like, there is a very high correlation of 0.81, but the mutation here is a little bit better, and but the takeaway is, yes, the mutation grader is a strong indicator of a test suite's fault finding ability. Next question, back to the goodness thing. Does student test quality improve? So let's get a better definition of what it is to be a good test suite. To find metrics, we looked at our learning outcomes, 2 of them. Number 1, learn to write a test suite that finds faults. Number 2, learn to check behavior of all code that is invoked. With the fault finding ability, we've already seen this. It wasn't as good, but I think I have explanations. In the mutant term, there was this additional component that we added to the testing phase. I didn't talk about it before because it's like pretty unrelated, but we said, wouldn't it be cool if the students learned how to bootstrap their own project and write all the boilerplate and gather dependencies? So we gave them no starter code. Whereas students in the coverage term, they had plenty of starter code. They had 4 starter tests. So the mutant term, the weaker submissions are pretty spread out, whereas the coverage term, the weaker submissions maybe are kind of pushed up. Also in the mutant term, it was our first time running it. We were afraid we were being way too hard on them. So we told them all on Piazza, the forum, hey, we'll just scale you all 20%. And when you see 100% on your grading sheet, you're not going to keep working. So maybe they just stopped, which either way, we can't show that the fault finding ability of test suites improved under mutation analysis. Oh well. Next, through the lens of learning to check the behavior of all code that was actually invoked. So here are some scatters. Along the x-axis, I have how much code was actually invoked. This is the code coverage score we're all familiar with. And on the y-axis, this is the fault finding ability of the mutation oracle. Again, mutation oracle scores. So how much behavior was actually checked. That means that anything that's down and to the right indicates code that was actually invoked but not asserted upon, at least correctly. And what's kind of interesting is students in the mutant term were more likely to correctly assert over invoked code. Nice. Next, do students strive to understand the specification better? Now, this goes back to that learning outcome of learn to refine a specification into a test suite. We would hope that students know the specification better, but unless we were quizzing them on it, which we didn't think to do at the time, I don't have a direct measure of how much do the students know the specification. So we settled for an indirect measure, which is how hard do the students try to understand the specification? And how we measured that was we just went on to Piazza and we counted how many times did the students ask a specification clarifying question. The belief is that the more that the students negotiate the requirements, the more litigious they are about, what does this really mean? Means the more intimate they are trying to become with the specification. And nicely, students in the mutant term were asked far more specification clarifying questions, both in total and per student. Next, does the velocity of implementation improve? Again, following the testing phase, when they pair up, they start building the thing, and we would hope that with tests that were validated by mutation analysis, maybe it would be easier to build the thing. There are a lot of different ways you could look at that. One of the metrics that we looked at was how many submissions did it take for the students to really get started, and how many submissions until they were doing well, their score in the first few submissions, and the rate at which submissions were helpful, because when you make a submission over a previous submission, the score can go down or stay the same or improve, and we want to see how many of those were positive deltas. But between the two terms, no real change. So mutation analysis did not show obvious benefit to implementation velocity. And lastly, what do student tests look like in practice under mutation analysis? Now, this one was more of an exploratory study. Students will try to game the grader no matter what. No matter what you do, they're going to try and build the test to match what you've given them, or the acceptance criteria. And because at the time we wrote this is no longer true, but at the time we wrote this, we hadn't seen any other courses employ mutation analysis to grade students. So, or on such a wide scale as autograder feedback. So we wanted to see how did that change what they were writing. And again, a lot of ways you could look at this, but the 4 things we looked at was how many tests are in the test suite, how many assertions are in those tests, how many keywords are in the assertions. And that might look weird, but I promise I'll explain it. And what kinds of assertions are being used. So firstly, fewer tests, which is kind of cool, I guess. Even if you were to compare with similar fault-finding ability ranges, students in the mutant term used fewer tests on average to implement the same test suite. Not necessarily a good thing or a bad thing, maybe a bad thing, but interesting. How many assertions are in the tests? Well, students in the coverage term didn't have to write any assertions at all to get 100%. So it makes sense that students in the mutant term were more likely to have 1 assertion. But what's interesting is they were more likely to have 2 or 4 or more assertions than students in the coverage term. Next is how many keywords are in the assertions. So assertions are not equal. They can check more or less of the underlying behavior of the code depending on their complexity. And Chai, which is the assertion library that we used in this project, lets you append or augment the complexity of an assertion by adding keywords to it. So if you want to check if the value of foo is the Boolean value true, it's expect to be true for. And if you want to check that foo is not null and not undefined and is an object and has a prop, at least one field, and that field has the name whatever prop is, that's 7 keywords. But between both terms, the complexity is pretty similar. Lastly, what kinds of assertions are being used? We should have a better graphic for this. But in the coverage term, there were 3 broad assertion categories which were really common. The first one being type assertions. So is an object an instance of some class or a subclass of some class? Or is it a primitive value of some type? And next would be error. So is a function going to throw or not going to throw? Or in the async world, reject or resolve. And equality, is A equal to B, or deeply equal to B. And in the mutant term, same most popular categories, but kind of cool is that students in the mutant term were more likely to use other assertion categories. So does an object contain some value, or does a list have a length above something? So what does student tests look like in practice under mutation analysis? Fewer tests, more assertions, low complexity, just like before. And more variety of assertions, which is neat. So in review, from the top, is mutation grader an accurate indicator of test suite quality? Yes. Does student test quality improve by a metric? Do students strive to understand the specification better? Yes. Does the velocity of implementation improve? We couldn't share that. And what does student tests look like in practice under mutation analysis? More verbose and more concise at the same time. Yeah, so that's all I have. Thank you.
All right. Are there any questions?
Hey, so fantastic talk. Thank you. So you mentioned that in the mutation version of the course, you did not give the starter tests to the students.
Yes.
How do you think it would impact the results that you're reporting? Had you either have a version of the course for the non-mutation people without starter code, or like basically give them equal settings? How would that have impacted the situation, you think?
Yeah, such as the penalty of action research, huh? I think it would affect a lot, really, I do. When we were designing this, it wasn't to be a paper. It was like, at the time, we were wanting both of these features in the course. I really do believe that the velocity of implementation is not going to change. Like they pair up and they have like TAs to help them out. I think you're going to come to a similar place in either case. I think that what was interesting was you might believe that with starter code, you would write fewer assertions. You might think that with starter code, you might write more assertions because you have something to model it off of. But with no starter code, they were still, I guess they were, or maybe that is because of that. Maybe they were more likely to explore the actual try documentation and see other. Anyway, I think that all of these things would change at least a little bit, but I don't think that makes this less interesting.
I have a question and an idea of which I want your opinion of. First, the question.
Okay.
Was there a difference between the way of how often students submitted their code to the author grader between the two terms? Like, did they submit more frequently or more? Like, was there a difference?
Okay, I genuinely don't remember this. This is something I should have written down for this. So they had the same restrictions of you can only submit every 6 hours, which they didn't like actually. Yeah, I don't know. Can you ask me again after so I can look this up? I can probably look it up from my computer.
Okay, and then the idea I had. So your approach was to manually create these mutants. But I was thinking, isn't it a good idea to write a reference testing suite and then use an existing mutant generator on your test suite and then use the mutants that you killed and use those to grade the students?
Yeah, that is another good idea. Well, one thing was we ran our test suite against the mutants and we found that we're not so great at writing tests either. So that's kind of interesting. I do think that is an avenue. There is kind of this, there are a lot of oddities in that, like this one test might actually be testing multiple behaviors, or like, the other way around, this one mutant is pointing at multiple tests. So trying to get something that's like kind of like a one-to-one relationship between those two and saying that this is the rubric I care about. Here are the tests. I want that to translate to that same rubric, but in mutants. I think that's not super trivial for a variety of reasons. But I do think that is an avenue, like just more work necessary.
Thank you.
Other questions from the room?
Yes, we were switching. You assume perfect specifications in this course. Do you consider that your specifications are not perfect in some way during this course?
Sorry, could you repeat the beginning of the question?
Yeah, you assume perfect specifications.
Yeah.
To write test cases against. If you look in practice of programming, you see that specifications are quite often incomplete, wrong, misinterpretable, all that kind of thing.
Yeah.
Do you take that in account while doing this course?
So I think that's a really important, I think for me, that's actually one of the motivators for curated mutation analysis. Because if you were to use just a general off-the-shelf mutator, and you have some code which is implementing undefined behavior, right? The spec didn't say X, Y, Z, but under the hood, the implementation is doing X, Y, Z. A general mutation generator is going to still generate mutants there, even though I didn't want it to. So to me, this curated mutation analysis allows me to look specifically at the lines that I know are testable. And although there is gray area and like holes in the spec, intentionally, those are not places that we're going to be generating mutants for. It'd just be unreasonable.
So another question maybe. So I was curious whether you looked at the setup code and the fixtures they used, like the examples they fed into the program. Did they get more complex? Did they get less or more?
Oh, that is another really good question. I don't know. Yeah, I think that should go under that last section. Now I want to know. Yeah, I don't know.
If you get like less or more assertions, you probably have like more or less complex objects they use assertions on, maybe.
Mm-hmm. Yeah, good question.
All right. There appear to be 2 questions in the chat online. Braxton, one of them, oh, it looks like Elisa has replied. Were there any issues found with plagiarism in this situation?
So this didn't unveil new kinds of plagiarism. Plagiarism is always a problem. If anyone has solved it, let me know.
Sure, you can copy our solution.
Sweet, thanks.
And the second comment, Braxton, is there's a reference to John Wren and Shriram Krishnamurthy's paper on exemplar, which is a integrated version of this sort of mutation testing into the IDE that students are using. So they call the task separating the wheats from the chaffs, where the wheats are the good implementations and the chaffs are the bad ones. So if you have not seen that before, that is a useful link to check out.
Cool, thank you. Exemplar?
Exemplar, example.
Thank you.
Are there other questions? All right, let's thank the speaker.
Thank you, everybody.